Good afternoon. My name is Frank Wessels. I'm CTO at MinIO, and welcome to our presentation using S3 Select to deliver 100x performance improvement versus the public cloud. Okay, most of you will probably be familiar with Amazon S3 as, obviously the de facto standard for object storage. And today, you'll find object storage being used more and more for all sorts of applications, including high-speed analytics. But today, I'd like to talk about sort of a newer addition to the S3 API, which is called S3 Select. So what S3 Select allows you to do is essentially, instead of necessarily retrieving the whole object from your object store, is to peek into the object and just retrieve a subset of the content based on certain criteria that you specify. This works for a couple of formats, amongst others CSV, JSON, as well as Parquet. Some of the advantages that this offers is that obviously this allows the operation to be faster. Because you are retrieving a subset of the information, it also consumes less network traffic, which in turn also allows you to use, for instance, more efficient and smaller compute nodes for jobs using less memory. So at MinIO, we have open sourced a package called MinIO/Spark Select, which allows you to integrate this S3 Select capability into your Spark stack and thereby essentially offloading your queries to object storage. Now, before I dive into the details of some of the optimizations that we've done for S3 Select, allow me quickly to introduce MinIO to you. So MinIO is a high-performance distributed object storage server really designed for petascale data infrastructure. It is 100% S3 compatible, meaning you can essentially take your AWS applications and run them on MinIO without any code changes. We've also taken the principles, essentially, of the hyperscalers to create a truly scalable architecture. At the same time, it is still simple in its nature, meaning it's easy to install, easy to use, easy to maintain, and everything. And also, we've put a lot of emphasis on performance. So some of the key algorithms in MinIO, for instance, erasure coding and hashing for bit rot detection, those are accelerated using low-level assembly instructions, and not just for the Intel platform, but also for ARM and recently Power 9 CPUs as well. If you look at sort of the global uptake that we've had, you can see it here. So pretty much, across the globe, and I think it's fair to say that MinIO is now the most popular and fastest growing open source object storage out there. We have over 15,000 stars on GitHub, as well as over 200 million Docker pools. So that's we're pretty pleased with that. I already mentioned that we put a lot of emphasis on performance. So if you look at our GitHub repositories, then obviously MinIO is the one with the most stars. But also we have some other repositories that have become reasonably popular. Some of them have to do with fast hashing techniques that we've accelerated using assembly. But also, we have developed a tool that is called C2Go ASM. And what this tool allows you to do is essentially to take optimized C code and sort of transport that into your Golang runtime. And interestingly enough, this tool is now also in use by the Apache Arrow team, or at least I should say the Go implementation of the Apache Arrow project. So they're leveraging C2Go ASM to get better performance for some of the stuff that they are doing. Getting back to S3 Select, one of the first things that we sort of looked at when we started to look at the sort of performance of these S3 Select operations is to kind of see where Amazon sort of is at, and actually some of the results surprised us a little bit. So we're actually running a S3 select query here on the same data set in 3 different formats, and it actually turns out to be that kind of plain old CSV is the fastest here. So it takes about 5.5 seconds to get the response from a 4 million row data set. JSON is a bit slower than CSV, which is kind of to be expected, because obviously JSON is significantly more verbose than CSV. But what is actually surprising is that Parquet is even significantly slower than JSON still, which surprised us, because obviously Parquet is a columnar format, so you would expect that to be more efficient for queries. But we'll get back to these numbers a little bit later. So when we set out to design how we could accelerate the performance of S3 select queries, we came up with the following high-level design. So essentially, there are sort of 3 phases in our query execution process. So the first phase is a, for CSV and JSON, a parsing phase. And for Parquet inputs, it will be more of kind of a loading / decompression phase. So once the initial phase is done, then the second phase of the process is the evaluation phase, where essentially, we execute the where clauses that you are running as part of your S3 select statement. And finally, the last step is the processing phase, where you sort of execute your select part of the query, which may either return you all the rows for the columns that you're interested in, or maybe do a count star or what have you. The code actually that we're going to show you later is actually available on GitHub, so it's in a repository called select-simd on GitHub as well. Now, when we started to do the performance thing, the first thing with MinIO being developed in Golang, so the go-to place to start with is the standard, CSV and JSON parsers. And whilst they are, pretty good for sort of small objects, as you start to scale into objects that are, gigabytes or even tens of gigabytes in size, having, hundreds of millions of rows, and every row having, 10 or 20 columns, you really start to see that kind of the garbage collected nature of Golang starts to hurt the performance. And actually, what we're showing here is sort of a benchmarking project that we've found, and it lists the performance of CSV parsers for different languages, and sort of we plotted out a few of them, and you can clearly see sort of a division between kind of what we call the garbage collected world and the non-garbage collected world. So if you look at kind of the greener cloud at the bottom of the screen, those are parsers in C, C++, or Rust. They're essentially almost 10 times faster than if you look at kind of the garbage collected world, where obviously Golang and Java are. So to basically get to a level of performance where we would like to be in terms of parsing speed, it was quite clear that we couldn't use sort of the standard Golang, CSV, and JSON parsers. And this led us to a design where essentially we map the gigabytes of CSV or JSON data almost in a kind of a read-only manner into memory, and then work directly off of that data without essentially ever trying to make secondary copies of that data. So this gave us basically a first performance boost, allowing us to parse data at roughly, say, 500 megabyte or half a gigabyte per second. Now, while that was good, at the same time, with some of the other performance work that we've done at MinIO for erasure coding and hashing, there we are achieving literally speeds of several gigabytes of memory, or even sometimes more than 10 gigabyte of throughput on a single core. So we weren't quite content with the kind of the first step of acceleration. So this led us to look at SIMD instructions. Now, for those of you who do not or haven't heard about SIMD, SIMD essentially stands for single instruction, multiple data. And in essence, what it allows you to do, it allows you to process large number of bytes in parallel using essentially a single instruction. Now, there's various flavors of SIMD instructions, but in this case, we're using the AVX2 version on Intel CPUs, which processes 32 bytes in parallel. And if you integrate this, you can very nicely accelerate, for instance, a delimiter or a separator detection operations, also for various bitmap operations in terms of handling and parsing. These instructions offer great instructions. Stuff like string compares or number compares, you can do those in parallel as well. So essentially, by implementing these SIMD instructions on top of the zero copy behavior that I showed on my previous slide, we were able to push the performance on a single core to close to 5 gigabyte per second. And with that, I not only mean sort of the parsing speed, but this is actually all the three phases that I showed in, I think it was 2 slides ago. So it's the parsing stage, it is also the where execution and evaluation phase, as well as basically the selection phase. So we're pretty pleased with that result, and we have also integrated these SIMD accelerations for S3 Select into MinIO. And then if you compare it to the results that I showed you a couple of slides earlier, you can get a pretty dramatic speed improvement. So literally where the CSV took over 5 seconds earlier on AWS, we can actually do it in less than a tenth of a second. So with that, I'd like to hand it over to my colleague, Chris Slater. He's going to show you a little demo where we're actually using a little bit larger data set. So it's going to be 3.5 gigabyte in size, containing 25 million rows. And we're running all of this in the cloud in the US East 1 region of Amazon. So we have MinIO server running using or with these SIMD accelerations on a C5 2x large instance, and also we'll be firing off the queries against both Amazon as well as MinIO. So Chris,
okay, great, thanks. Now, let me just get set up here, switch quickly over to our screen here, and unfreeze. They gave me this neat button where I could freeze the display output here. Anyway, Chris Slater, I'm an architect. I work at MinIO. I'm glad to see you all in the room. I assume because you're here, you run Spark. Are you running, I'd be curious to know how many people are running Spark in a private cloud, in a private data center? How many of you run, and how many of you know about this S3 Select? Are you taking advantage of S3 Select today to do filtering on your data set? So this is a powerful tool. It's available to you today in Amazon, and now because we're 100% Amazon API compliant, we've incorporated it into our product. My role here is to do a drag race. We're going to do a race up here. On the top window, I have Amazon. I'm going to do a query here in which I'm going to do a SQL query. I'm going to select count from an S3 object. I'm going to look for something called FERR, explain to you what that is in a minute, and it's going to be running against AWS in the S3 Select benchmarking bucket. It's pulling from the parking citations CSV file. So this was, how big, Frank? This was 3.5 gigabytes in size, millions of records. 25 million. 25 million. So we purposely chose that because this is all the parking citations from Los Angeles for the past while. So if any of you have been driving a Ferrari in Los Angeles, your parking ticket's in here, and we're gonna find it now. So in the bottom window, I'm gonna run a command here, the MC head command, and I'm just gonna show you the actual structure of this data. These are the first 10 couple of rows. You'll see a number of records going across columns. We're going to choose the make column, which is right here. Here's the make column, and they use a 4-letter acronym, or they actually use Honda's HOND, GMC, Nissan, etc. So we're going to start here. The query is going to count the number of rows, so we can see the number of rows that are returned by each query. This is the same jump box running in Amazon and connecting to different instances of S3 object storage. One is Amazon, one is MinIO. So with that explanation, let's get started. We've got the little time command here. We're going to see how long this takes inside of Amazon. At the same time, we're going to run this very similar query here, where we're going to do a query, select count of from S3 object, where make is Ferrari. But this time it's my MinIO and parking citations. And let's see, oh, it's done already. Oh, wait. It happens in a fraction of a second, and we're still waiting for Amazon to come back. This kind of surprised us. I know, Frank, when you first ran these test results, this came as a surprise to you how much faster we are. We expected to be a little bit faster. We didn't expect to be, what, 100 times faster in this query?
Yep.
So we're going to wait for this to be done. We can go and query for other things like Lamborghini owners. They're notoriously bad owners. We could see where they are. But basically, the query is the same. Make is something here. So this time, we're done up there. 46 seconds to run their query. In ours, we're 0.292 seconds pretty consistently. Now let's grab all the records. So same query again. You notice the return result, was 3897. And for us, it's 3897 each time. The number of rows that comes back in that count statement is exactly the same. It's the same data set. So here, let's move back a little bit, and I'll give you more of a feel for how fast or how slow Amazon is this. Now, we've also tested our S3 storage, just doing puts and gets and retrieving objects and putting them, and that happens to be approximately the same performance as Amazon. So they're certainly very fast. We are focused on performance at MinIO. So here we're going to do this select again, and here we're going to run it in MinIO. MinIO. That actually is the entirety of my demo, and Amazon is still running up there. So let me turn it back over to you, Frank, and I'll push present, and off we go.
OK, thank you, Chris. OK, so yeah, thanks for showing the demo. Sort of what's next, the initial focus of this work is actually on CSV data, so we'll be finishing that work still. What you see here is actually still relatively new and relatively early work, but I think it shows the potential of combining these two behaviors, zero copy and SIMD, together to really supercharge the performance. We will also be adding support for both Parquet as well as JSON, and actually for JSON, we will be integrating a very interesting project called SIMD-JSON, and as you can probably figure from the name, it also uses SIMD instructions to leverage JSON parsing, and they're getting gigabytes of JSON parsing per second. So that will be a great fit for this kind of stuff. Another development that we'd like to look at is actually AVX 512. So thus far, the results have been obtained with using AVX2. But now, AVX2 or 512 is out there, which is essentially double the width in terms of its pipeline and parallel capability compared to AVX2. And actually, we've already got some nice results on our erasure coding. So there, we actually have another 4 times speed up over our AVX2 optimized code. So there's definitely great stuff there that actually we haven't really touched yet. Some other stuff that is interesting is more some dynamic code configuration, which ties into some of the C2GoASM stuff that I showed later. But that's a little further out. Also, one last thing I'd like to point you to is it's combining this sort of processing level of performance with high performance object storage in terms of running your object storage on SSD or even NVMe boxes, or for instance, we can even run on power CPUs with a PCI Gen 4. Really saturating dual Mellanox CX5 cards, so delivering tens of gigabytes of throughput per second. Now I'm starting to run out of time, so I'll wrap up quickly, but sort of getting back sort of the benefits of using S3 Select in terms of Spark, again, are that you can run much faster queries than retrieving the whole object. you can minimize your network traffic, and also your computing needs can be significantly reduced by having less memory requirements on the compute nodes. We will definitely be doing some further testing in terms of how does, say, not using S3 select compare to using S3 select. So yeah, stay tuned for some further benchmarking that we will blog about to see how that works. With that, I'm essentially out of time. So thank you for your attention. If you have any questions, feel free to ask me here, or I will also be at our booth. So thanks for your attention.
Thank you.
All right. Thank you very much.